Well, hi there. Today we're going to be talking about finding the area between two curves using integral calculus. Our opening animation did a nice job of visualizing how exactly we're going to accomplish this feat. To find the area between two curves, we're just going to take the area underneath the top curve and subtract the area underneath the bottom curve. Or if we don't have an obvious top and bottom curve, we'll just convert everything to y's and do the area under the right curve minus the area under the left curve. Of course, we can always accomplish this using two or more integrals, but thanks to the properties of integrals, we can make things more efficient and cut it down into just one single integral. You can see that on the screen here. To find the area between two curves, we either do the integral of the top minus bottom, or we do the integral of the right minus left. Now, because we're looking for a numerical answer, that means we're going to have to use a definite integral. The limits of integration for finding the area between two curves are always going to be the points of intersection unless they are otherwise specified. The basic process is very simple. Just define your top curve, define your bottom curve, and then use the fundamental theorem of calculus to evaluate the integral. Now, I could flap my gums at you all day, but nothing supplants the power of practice. So let's take a look at our example problem below. Alright, so the question reads, let f of x equal x squared minus 2x plus 2, g of x equal negative x squared plus 2x plus 2, and then they tell us that the two functions intersect at the points 0, 2 and 2, 2. Finally, it tells us what it wants us to do. Find the area of the region bounded by the two curves. This is a nice, clear application of the formulas that we outlined above. So the first thing we need to do is define our two functions. Figure out which one is the top and which one is the bottom. Then, we're going to plug into our integral and basically just simplify and evaluate. It'd help to know which graph goes with which equation. We can take a look at the first term in both. I see in f of x that I have a positive x squared, which means I have an opens up parabola, the blue one. And in g of x, I have a negative x squared, meaning I have an opens down parabola, or the orange one. Let's label these so we don't get confused. The blue one was f of x, and the orange one was g of x. The question wants us to find the area of this region here bounded between the two curves. Since we have a clear top and bottom function, we're going to use the first integral listed above, the one that goes from a to b of the top curve minus the bottom curve, and then we're going to put dx like that to make sure that people know we're taking the antiderivative with respect to x. Our top curve is the orange one, that's our g of x function, and the bottom curve is the blue function, that would be f of x. A is the x value of the left point of intersection 0, and b is the right point of intersection's x value 2. Now we can replace our general integral with the specific information for this problem. Our integral is going to go from 0 to 2, and then I'm just going to zoom out so I make sure I get these formulas right. We first need our g of x function. That would be negative x squared plus 2x plus 2. And then we always need a minus in between them. My f of x function is x squared minus 2x plus 2. We'll have dx, and notice how I put my two functions in parentheses. This is going to help me make sure I avoid making mistakes. Why? Because this negative sign needs to be distributed into the second parentheses. So what we're going to do is drop all the parentheses and then combine our like terms and anti-differentiate, if that's even a word. I think it's a word. We can just get rid of the first parentheses, but then we have negative x squared, negative becomes positive 2x, and then minus 2. And now we combine our like terms. We're going to have the integral from 0 to 2. Then we have negative 2x squared. Our 2x is combined into 4x. And then the 2's cancel each other out, so we're left with just dx. Now we take the antiderivative of our two terms and evaluate. The antiderivative of negative 2x squared is negative 2/3 x to the third. And the antiderivative of 4x is 2x squared. And we are evaluating this from 0 up to 2. Now for a little substitution and arithmetic, we're going to plug in 2 for x. So we get negative 2/3 times 2 to the third plus 2 times 2 squared. And that's the first part. And then, notice how we have a 0 and then 2 x's. Well, anything times 0 is just 0, so this whole thing's going to come out to 0 on the right. That's awfully convenient. Thank you, universe, for the handout. Now, 2 to the third is equal to 8. And then in our second part here, 2 to the second is 4. Evaluating these is going to give us negative 16 thirds plus 8. Don't be scared by the fractions. Watch this. 8 times 3 is 24, minus 16 gives us, drum roll please, 8 over 3. Oh, we did it! We found the area between the two curves. It's 8/3 square units. So you see, that wasn't too hard. Of all the things you learned in calculus, this is maybe one of the easiest ones. All you have to do is figure out which function is the top function and which one is the bottom function, or, if you don't have a clear top and bottom, which one's the right and which one's the left. Once you've classified that, it's just plugging into the formula and doing all of the FTC work that you're already really good at by the time you get to this skill. Obviously, if you have any deficits in that department, or maybe you're a little bit troubled by the arithmetic that we did here, now's a really good time to shore those things up. You can't really get from the start to the finish of these problems without having those skills mastered ahead of time. And hey, that's it! What a breath of fresh air after all the work we did with rectangles and trapezoids and things like that. The list just goes on and on and on. But, if we're thinking ahead here, if we do stuff with area, doesn't it make sense that we would do stuff with volume? Uh-oh. I guess we'll see you next time. Bye!